So 2.4 atomic structure. What we already know about an atomic structure are very few basic things. We already know that John Dalton was a teacher who gave us a few points about the atomic theory, that it was a solid, indivisible set of particles, probably the smallest particle which every substance is made up of. He was wrong with solid, he was wrong with indivisible too, but the rest of it was somewhat correct. But definitely, it led us into a direction where we could work our way out with correct things. And of course, with first atomic theory, there was bound to be some suggestions, some comments, some more work on the way to get everything in the right direction. J.J. Thomson discovered electrons, somebody discovered protons, another person discovered neutrons, and from there on onwards, we got to know that the atom is composed of three subatomic fundamental particles. I mean, there are more than 100 different subatomic particles we have discovered for so far, but we call them as fundamental particles since they're a part of every atom, right? So there are some subatomic particles which are a part of one atom but not a part of another, which are maybe a part of one element but not of another. But these are actually the fundamental ones. So we ask the students to start with these ones as they are the easiest ones to consider. Now, we do understand that the nucleus is the center of the atom and it contains almost all the mass of the atom. Atom was consists of three fundamental particles: proton, neutrons, and electrons. We do understand that electrons are considered to be the smallest particles by mass. We do understand that protons and neutrons are a part of the nucleus. We also understand that atom is largely empty space. So all of that is completely understandable, I guess, and it's easy, something you're already done with too, right?
Yes, sir.
Okay. Then what did we started to do? We started thinking about a way to measure the size of atoms. Since atoms are very small, uh, so it was almost impossible at start to look at an individual atom or weigh an individual atom. What we could always do was comparison. So we started off with a sophisticated instrument we called mass spectrometer. And mass spectrometer was there for a purpose that we were able to compare the masses of different atoms, not one atom at a time. Of course, we took a huge number of atoms together and we actually put up a standard. The standard was carbon 12, and we measured every element as per carbon 12's mass, whether it was uh, heavier than carbon 12 or lighter. For example, when you look at periodic table, you find certain pieces of information out of which we have created this table. As soon as you look at this table, you get to see a few most common elements along with their atomic symbols and their masses. Carbon with a capital C, mass 12, hydrogen 8, mass 1, oxygen O, mass 16. So, as I just told you a couple of moments earlier, we took this as standard, all right, and we compared every other element with it. So if the mass is less than 12, we got to know that that specific element is lighter than carbon. And if the mass was greater than 12, like these ones are, we got to know that they were heavier than carbon atoms. Make sense?
Yes, sir.
Good, good. So I think this is pretty easy. For a value greater than 12 will be heavier than carbon. For a value greater less than 12, it would be lighter than carbon atom. This is just a touch of a topic so that when we pick up the same topic of mass spectrometer in A-level classes, the student should have an idea what we are talking about, just an idea, right? So coming back to the structure of atom and the nucleus and the fundamental particles, they're going to give you a few ideas. To begin with, there is a simple comparison. Size of nucleus as compared to the size of rest of the atom. Now these lines are pretty good in giving you an idea that if the atom were the size of a football stadium, the nucleus would be at the center spot and would be at like the size of a pea. which actually clarifies that the most of the atom is empty space. Make sense?
Yes, sir.
Good, good. Now this diagram gives us a pretty good idea. They tell us that nucleus is the exact center of the any element's atom, and this consists of protons and neutrons. Proton has one positive charge. We write it like this. It has a mass of 1 unit. Neutron has no electrical charge. We call it neutral. It also has a mass of approximately 1 unit. The electrons are not present inside the nucleus. They're outside the nucleus. They're present in specific pathways that we call shells or energy levels, and they keep revolving around the nucleus in their specific energy levels. So when we talk about electrons, they're the lightest mass. They have one negative electrical charge, and they're so lighter in mass that we say they hardly have any mass, or we simply use the word negligible for their masses. All of this information is actually covered at a table at the bottom of the page, page number 42. You'd notice that proton is, and I'm going to add a few things to the table. I hope you have the hard copy of the book in front of you. You have a pencil ready so that you can make the changes I ask you to. Can you?
Ji, sir.
Good, good. Let's be ready. There are places in the book where we are going to put proton as a small p in terms of symbol, or neutron as small n in terms of symbol, and electron as small e in terms of the symbol. Most of the time, what we're going to do is that we're going to represent electron with e negative and proton with p positive. Proton with P positive is something that you are gonna see in the book, but electron with E negative is gonna be something that you will see mostly. You'll find the same symbols over here, here, and here. Now you notice they have a 0 on top of N, which actually gives you the idea that it does not have a charge. So this is about the relative charge. Proton has a positive because of +1 charge. Electron has a negative because of a -1 charge. Neutron has a 0, and I usually ask my students to write neutral in brackets next to it. But here gives you the idea that either neutron is uncharged or it's neutral. Both means the same thing. Moving
Ji,
on,
sir.
let me tell you this is relative charge. This is not the absolute charge. What is relative charge? What is absolute charge? When I use the word absolute, I am actually talking about the charges of the species, whichever one we are discussing. For example, if we're talking about proton, or neutron, or electron, when I use the word absolute charge, that means the exact charge on them. Now, let me tell you the exact charge on a proton or an electron is a pretty small value, something like this, coulombs. This is for coulombs. All right. Now, this is a very small value since 10 is raised to power minus 19, which means it's 0.0000, and then there are 18 zero after that 16022, which is a very small value, right? So what do? We can't keep coming up with this value all the time and writing so complicated numbers all the time. What do? We actually relate them to one another. We came to know that the charge on proton and the charge on electron are almost equal, exactly equal if you want to use this phrase at this level. So we, instead of using 1.6022 into 10 raised to power minus 19, we use simply 1. That's actually pretty easy to calculate. And students can really work with it very easily. Actually, it comes to every student, scientist, teacher, or researcher on the planet. We did the same with math, relative math. All right. So
Okay,
what
sir.
happened that the mass of proton and the mass of neutron, they differ very slightly. Since they differ very slightly, they both came to be 1 at the relative table. And since this mass was very small, it became 1 over 1840, and we used the term negligible for it. Which means when we're going to calculate the masses of the atoms, we're mainly going to add up protons and neutrons, and that's about it. We're not going to care how many electrons it has, since it's it won't give a noticeable contribution towards the mass. Make sense?
Yes, sir.
I guess you're still not clear about relative masses. So what do we do is that if we have different numbers, let's say we have number 2, and then we have number 2.01, and then we have number 0.012, we can divide them by a standard number. Let's say I pick the standard number to be this 2. And I'm going to divide every of this number with the same one. What's going to happen is it's going to be 1. This one is going to be 1.005, which is going to be approximately 1 again. And this one's going to be 0.006, right? So what happened is that this became the fraction for the electron. These two, 1 and 1, became the number over here. That's the idea behind it. It's actually a mathematical way of easing up the numbers that we commonly use. Hence the term relative mass or relative charge. I hope that makes a little bit more sense, if not complete sense.
Ji,
Right?
sir.
Okay, good, good. So the location in atom is something pretty easy. We know proton is a part of the nucleus and is part of the atom. So is the neutron, but the electrons are revolving outside the nucleus. Okay. There's a easier example over here. An atom of gold will consist of 79 protons. It could also consist of 79 electrons, but 118 neutrons, which gives us the idea that the number of protons and number of electrons are equal for an atom. Why is that so? There is a very important point, has been used for past paper exams as well, that a single atom is electrically neutral. It has no overall charge. This means that in any atom, there must be equal number of protons with equal positive charges and equal number of electrons with equal negative charges. So the total positive charges and the total negative charges actually balance one another. The positive charges are present in the nucleus due to protons, and the negative charges are present outside the nucleus due to the orbiting electrons. Let's clarify that with the example given on the top of the page for a structure of helium atom. Now we have been given helium atom. The protons are given with this red plus charge. These are the neutrons with purple color, which have no charge. And these crosses are actually electrons. So you'd see they have a total of 2 protons. The overall charge would be plus 2. Every proton has 1 charge. 2 into plus 1 is equal to plus 2. And there are a total of 2 electrons, which means the overall charges are going to be minus 2. All right. So what happens? In math, plus 2 minus 2 is equal to 0. We say that the charges balance one another. So the atom has no overall electric charge. That's why whenever we write an atom, we don't write anything on top of it. Why? Because this is usually 0. For an atom, this is supposed to be 0. However, this number may change for an ion. And I hope you're familiar with that.
Yes, sir.
Now, you know, ions are of 2 types, the positive ones and the negative ones. And they always have an imbalance of protons and electrons. I hope you're familiar with the fact that positive ions have more protons than electrons, and negative ions are vice versa. They have more electrons than protons. So the net charge
Yes.
on a negative ion is negative, as the name suggests, and that of a positive ion is positive, of course, as the name suggests too. Right? That's why
Yes, sir.
we say atom is a neutral species, but ions are electrically charged. So atoms have same number of protons and electrons, but ions will not have same number of protons and electrons. And that's why we have different terms, atom and ion. If that makes sense, let's talk about the 2 most important numbers in an atom. Shall we move on?
Yes, sir.
Great. Now, proton number or atomic number is the first most important number about an atom. Actually, to be honest, this is the identity of the atom on which the whole periodic table is based. And actually, that's the basis of chemistry as well. Now, proton number, which is also named as atomic number, over here is the number of protons in an atom. And any element, any atom in an element will have the exact same number of protons with the atoms of the same element. But it will always have different number of protons in case if of a comparison with a different atom. What does that mean? Hydrogen will always have one proton no matter which atom of hydrogen you're going to take. So if you compare two different hydrogen atoms, number of protons are always going to be the same. But if you compare hydrogen with a helium atom, the number of protons are always going to be different. Why? These are atoms of two different elements. So number of protons is actually an identity of an atom which always differentiates with other atoms of other elements. This is denoted by Z. The name is proton number, atomic number. Every different element on the planet has a different atomic number. But there is one important point. The imperative of this point is about the nucleus and the subatomic particles in it. Protons do not only make up the mass of the atom, and they're not the only ones in the nucleus. Neutrons are in there too. They also contribute towards the mass. So when we talk about mass or mass number, we also call it Nucleon number. Remember, anything residing inside the nucleus will be known as a nucleon. So protons are nucleons. Why? They reside inside the nucleus. Neutrons are nucleons. Why? Because the same reason they also reside inside the nucleus. Any subatomic particles which resides inside the nucleus is a nucleon. Nucleon number is the number of protons and neutrons in an atom. This is given by symbol A, and this is also considered as a mass number. Now, these two make up the mass of an atom. Why? Because in this case, we had this exact term which makes electron sort of ineligible for the mass number calculation, at least at this level. Make sense?
Yes, sir.
So what do? Whenever we have an element to write, we write it like this. The symbol of the element on its left bottom, it's Z, which means the atomic number or the proton number. On its left top, it's A, which is the gas number or the nucleon number. You can see the example for lithium 3 and 7, for carbon 6 and 12, for oxygen 8 and 16, for uranium 92 and 238. So if you go on with the periodic table, you're going to see hundreds of examples, which actually makes the whole idea easier for us. There are always two numbers with an atom, and giving you the easiest of tips, the smallest number is always the atomic number, and the larger number is always the mass number. Make sense?
Okay, sir.
So you never need to be confused about it. Even if they switch the numbers, there are some periodic tables you're going to find on the internet in which the numbers are switched. The A is written beneath and the Z is written up top. Don't worry. Again, the tip remains the same. Smaller number is the proton number and bigger number is the nucleon or mass number. That's how it is. And
Yes.
when we need to work our way with number of subatomic particles from these two numbers, proton number and nucleon number, it's pretty easy. Now let me tell you that from proton number, we get to know the number of protons in a nucleus. So much so we also get to know the number of electrons in the nucleus, which is not mentioned over here, but definitely something that needs to be mentioned. And it is actually mentioned over here. right? For number of neutrons, we have the simple formula. Smaller number getting subtracted from the bigger one, A minus Z. This gives us number of neutrons, right? So let's practice,
Yeah.
shall we?
Yeah.
So you have a few atoms over here. Let's start with lithium. How many number of protons are there in an atom of lithium? Li. Protons.
3.
Good. Number of electrons.
Also 3.
And number of neutrons.
Um, Kelvin.
Sorry, I didn't get that.
Kelvin.
No. Remember the formula. Smaller number is subtracted from the bigger number. So 7 minus 3 is
4.
equal to 4.
4.
Great. Let's do it for carbon. How many neutrons are there in carbon? Neutrons.
6.
Good. Now, you have four symbols: lithium, carbon, oxygen, and uranium written in front of you. Pick the element or elements which have the exact same number in terms of their electrons, protons, and neutrons. I mean, their number of electrons are equal to their number of protons are equal to their number of neutrons. All three numbers are equal. Pick the atoms.
Carbon and oxygen. Carbon and oxygen.
Carbon and oxygen. Great. Good. I hope now you guys get the idea, right?
Yes, sir.
Okay. Good. Good. So let's move on. And to give the same idea, you have a huge table at the bottom of page number 43, which discusses a lot of atoms. Column by column, you have the name of the atom, then the symbol, then atomic number C, mass number A. And if these two numbers are given to you, you can always calculate the number of subatomic particles. Actually, if you copy the atomic number stuff in the protons and the electrons line, that's good enough. Only for neutrons, you need to go with the formula and subtract the numbers. Good enough?
Yes, sir.
Students were usually asked to fill tables like these back in 2012 and 13 papers, but questions like these are still considered as a part of the paper. And we always say to our students that these are the easiest kind of questions. These are the questions which should give you pet marks. You shouldn't be making any mistakes, since 7 minus 3 or 12 minus 6 or 18 minus 8, 16 minus 8 shouldn't be something difficult to do, right?
Yes, sir.
That brings us to our next topic for today, isotopes. Now, when we started measuring the atomic masses of some elements, using the mass spectrometer was a little puzzling. Even the elements, even the atoms of the same element had different masses. How was that possible? It brought us up to a point where we were able to bifurcate them using the term isotope. We later came to know sorry. Okay. So we later came to know that isotopes were having different and confusing masses. sorry, getting back to it. So we later came to know that the isotopes were giving it confusing masses because there were different masses for even the same atoms. So what was different in those atoms? It was actually different number of neutrons. Let's take a few examples. The examples are given on the next page, page number 44. There is a huge table at page number 44. Let's start from the top of the table. The first example we usually take in O levels or IGCSE is hydrogen. Hydrogen has three isotopes, respectively named as hydrogen or protium, then deuterium, and then tritium. What's the difference? When it comes to proton, there are no differences. Take a look. All three have the same number of protons. So it was not the proton number or atomic number which had the difference. All three had the same number of electrons, one each. The only difference was among the number of neutrons. The first isotope, hydrogen itself, had no neutrons. The second isotope, deuterium, had one neutron. The third isotope, tritium, had two neutrons. So it was actually the number of neutrons which was making the whole isotope heavy. So what did we came up with? For the starting isotopes, we had their separate names. That's understandable. But since there are so many isotopes around the periodic table, we started coming up with different techniques of writing them. So how can we write them? You can write them like this: hydrogen dash 2 or dash 3. I mean, name of the element and then its mass number for any of its isotopes. Or we can write it like this: hydrogen 1, hydrogen 2, or hydrogen 3 for respectively the first, second, and third isotope. Or we may write it like this: H1, H2, H3, or H11, H21, or H31, like written over here. So these are all the ways to depict an isotope. Please ensure that you go with the convention followed by every scientist, student, or teacher on the planet and not discover a new convention of your own, right? Whole name hyphen mass number, symbol hyphen mass number, or symbol written with A on top and Z at bottom, or just simply A on top without a Z. Any of these may work in successfully mentioning an isotope. Let's take a few more examples. Carbon has three isotopes, 12, 13, and 14. Of course, from here we know from A minus Z formula that the first one has 6, second one has 7, and third one has 8 neutrons, respectively. Neon also has three isotopes, 20, 21, 22. So far, we have discussed about three elements, and all three of them has three isotopes. Please do not assume that the periodic table is filled with three isotopes. That's not the case. Different elements have different isotopes. There are elements which only have a single isotope. They don't have any kind. There are elements which have higher number of isotopes, for example, 14 isotopes or 16 isotopes or 12 isotopes or so on. So chlorine has only two isotopes, Cl35 and Cl37. Yes, you were about to ask something?
Yes, sir. I was asking that do we have to remember the proton numbers and neutron number and electron number for all of these? Like, do we have to learn it?
No, of course not. Okay, I clarified this table that if you get these two numbers, and which you're definitely gonna get because you're gonna have a copy of the periodic table at the end of your paper, so why do you need to remember all these? Since this whole line is copied as such into this line and into this line, only in this line you need to go with A minus B formula. So if you have these numbers in the periodic table, that's actually there for a reason. And you're getting a copy of the periodic table at the end of your paper, so that is going to help you with it. So no need to memorize all the isotopes here that you confront with in the book. That simply is against the rules of IGCSE or O level. See,
Okay.
it's not about cramming. It's about understanding and critically thinking how to use the most important numbers or identifications of an atom when they are given in the periodic table in front of you. The question is on the one side, the referring periodic table is on the other. How can you take the data out of the periodic table and turn it to your advantage, use the values in the question, answer the question appropriately? And that's what you're supposed to do. Make sense?
Okay, sir. Yes,
Great.
sir.
So if you get the point, let's move on. And it always gives my students ease to know that you're not supposed to cram a whole lot of subatomic particle numbers or mass numbers or atomic numbers. You know you're not supposed to do that. Yeah, with frequent usage, you are automatically going to remember the atomic numbers or the mass number of the first 20 elements or the elements we confront with most of the time. But that's not like cramming. It's just because of the frequent usage. And we explain the same thing to students. Now, you might have seen a few important things over here. You might have seen this small symbol A and A over here, or this word written next to carbon 14. So when we use the word A and A, we are actually referring to a radioactive isotope, which I'm going to define later. But when we use the word trace, it means the element is pretty rare on the planet Earth, or it means that they are found in very, very low amounts on the planet. Might be a part of the atmosphere, might be a part of Earth's crust, might be a part of any environmental portion around us, can be a part of rocks or a part of water or a part of air or even a part of our body. All right. So let's go and define isotopes and some important relative stuff about it. So I'm going to go with the key definition box at the bottom of page number 44. Isotopes. What are they? Atoms of same element. They have same proton number but different nucleon number. That's one way of defining it. The other way of defining it is in the first bullet point. Atoms have same number of protons and electrons but different number of neutrons. Both of these are considered as two different definitions of isotopes. Both are correct. Both are going to get you good marks. Moving on, isotopes of an element have the same chemical properties. Why is that so? Because they have the same electron structure. So it does not matter that it was the first isotope or the second or the third, because they are going to react chemically in the similar way. Now, some isotopes have unstable nuclei. These are the ones for which I was using the word radioactive isotopes or radioisotopes. They emit various forms of radiation. Let's discuss it a little bit more. Isotopes of an element have the same chemical properties because they contain the same number of electrons. Number of electrons in an atom actually decides the way how is it going to react with other atoms, how is it going to form bonds. However, there are some properties which are different for different isotopes, but those are physical properties. Those actually depend upon the masses of atoms. And therefore, other properties such as density, rate of diffusion also vary because they are dependent on the masses of atoms. I hope you understand from physics that density is equal to mass over volume, and this is dependent upon mass, so the value of density is different for different isotopes. That's why he's talking about it like that. Tritium and carbon 14 less the difference between the physical properties. They are radioactive, they emit various forms of radiation, and I'm going to explain that a little later on the next page. So what happens is that the neutrons and protons in nuclei causes them to be unstable. The numbers are differentiating too much. Nuclei break up spontaneously without any external energy being supplied. They emit certain types of radiation. We call them radioisotopes, and we're going to discuss them in the topic of radioactivity. Before we get to radioactivity, we have a small topic in between, that is relative atomic masses. Again, the term relative, which means we are going to compare the masses of different atoms. With what? With the atom that we have already put as a standard. Now remember on the previous page when I was talking about a sophisticated apparatus, mass spectrometer, I told you that we took carbon 12 as standard. Now this very well explains what this word meant. Carbon had three isotopes. One was carbon 12, one was 13, one was 14. Not 13, not 14, but carbon 12 is the standard for comparing the atomic masses of different elements. So what do we do in relative atomic mass? Actually, relative atomic mass is the average mass of naturally occurring atoms of an element on a scale where carbon 12 atom is exactly a mass of 12 units. Since carbon 12 atom has exactly a mass of 12 units, because of this accuracy, we put it as standard. There are other reasons too, but we go with this reason alone at this point in IGCSE. But that's not the main topic or the main concern. That's just the point I was trying to make to get you to calculate the relative atomic mass. We're going to go with the example of chlorine over here. All right. Before I go with this example, I'm going to go back to the previous page, page number 44. And on page number 44, the table gives you the details about chlorine. Take a look. Chlorine has two isotopes. One of them is 35, one of them is 37. And next to it, you'd notice the percentage abundance. On this planet, we find 75% of the time the isotope we encounter are of chlorine 35, and 25% of the time we encounter the isotope which belong to chlorine 37. What's the difference? Both have 17 protons, both have 17 electrons. It's the number of neutrons that are different, which are 18 and 20 neutrons respectively for chlorine 35 and chlorine 37, which means 35 has a different mass, of course 35, and 37 has a different mass, which is of course 37. Now, what are we going to do? We're going to take an average for relative atomic mass. Since we do not put different isotopes in the periodic table, as you might have seen chlorine just once in the entire periodic table, if there were two isotopes, we're not going to put chlorine twice. Since there are three isotopes of hydrogen or carbon or neon, that doesn't mean we're going to put hydrogen in the periodic table three times due to three different isotopes. That's not how we put it. If that's not how we put it, how would you know which exact isotope mass are we going to write in the periodic table? If we consider any one of them and neglect the others, that won't be fair, right? So we need
Yes.
a weighted average. देखिए तीन आइसोटोप्स हैं periodic टेबल में सिर्फ एक एटम एक दफा लिखा जाता है फर्क नहीं पड़ता उसके तीन आइसोटोप है या 10 है उसके नीचे कितना मैथ लिखेंगे पहले का दूसरे का तीसरे का दूसरे का लिखेंगे तो क्यों लिखेंगे दूसरों को खास है ना in order to give all of them a fair chance we came up with the term relative atomic masses and that term we have a specific formula in order to calculate the relative atomic mass what do we consider the average of its naturally occurring isotopes. You'd notice mass of the first isotope multiplied by the relative abundance of the first isotope added to mass of the second isotope multiplied by relative abundance of second isotope added to mass of the third isotope or the relative abundance of the third isotope, so on and so forth. We're going to go with all the isotopes possible and we're going to go with the addition of a big term. When we get this term, what we usually do is that we divide this term by 100. Since at the start of this experiment, we considered 100 atoms. That's why we were using the percentage. So every mass of one atom after dividing them by 100 gives us the value 35.5. Make sense?
Yes, sir.
If that makes sense, you can definitely find out the relative atomic mass for any other example. And I would really like to see if you can solve the example for neon. We have three isotopes. 20 is 90.5% abundant. 21 is just 0.3% abundant. and 22 is around 9.2% abundant. What is going to be the relative atomic mass of neon?
Okay, sir, I will do it.
Can you just keep going with the numbers, telling me that orally instead of writing it, if that's possible for you?
Yes, sir. First,
Go
we're
ahead.
going to write the brackets and we're going to multiply 20 with 90.5,
Correct.
and then
And
we're going to add it, and then we're going to use another brackets for the second one, which is 21 multiplied by 0.3, and then we're
good.
going to add it, and in the third brackets we're going to add the third one, which is 22 multiplied by 9.2.
And what
After
are we
finding the
going to do
value,
with the whole answer?
we're going to divide it with 100.
Are the sum of these three values 100? Means have you tried adding 90.5 plus 0.3 plus 9.2 is the total 100? We only divide it by 100 if the addition of these three is equal to 100. Is it 100?
Yes, it is 100.
Okay. Keep a note that we divide it with the number that these add up to. If they add up to 100, we're going to divide by 100. If they add up to 98, we're going to divide by 98, so on and so forth. Make sense?
No, sir, this was a little.
Sorry?
Can you repeat it again? Can you please repeat this again?
Yeah. What I'm trying to say is that you divide them with the number that the relative abundance adds up to. Since this entire abundance adds up to 100, that's why we divided them with 100. If in any case the relative abundance adds up to 98, kindly divide the whole thing by 98 and not by 100. Make sense?
Yes,
So
sir,
you
but
are
for
supposed to divide them by the sum of overall abundance that you get. Since we knew for this example that the overall abundance is going to be 100, we assumed for 100 atoms and divided it by 100. If in the case if that's not equal to 100, do not divide it by 100, divide it by that number. Let's say it's add up to 98.8, divided by 98.8 and not 100. That's where you're not going to get it correct. It's not that the assumption of 100 atoms that gives us the value 100. It's actually the sum of the relative abundance of all the isotopes over here that we need to divide it with. Make sense?
yes, sir, I got it.
And only then we can get the right answer for the average, because that's a weighted average. When you're going to do it with neon, you find out that your answer is around 20.18 something,
Yes, sir.
which tells us that you are capable of solving any question related to this relative atomic masses, or AR, and its calculation. All right?
Ji, sir.
Great, great, great. So